Welcome to lesson number 2 of the NumPy crash course. In the last lesson, we got a sneak peek of what NumPy arrays are capable of. Let us now direct our full focus towards the n-dimensional array. Generally, the n-dimensional array is homogeneous. That is, the items that it's composed of are all of the same type. An n-dimensional array is defined by its shape and the item that it's composed of. The advantage of all items being the same data type is that now you know every item has the same size block of memory. Each block of memory in the array interpreted the same way. This makes it easy to determine the storage size required for the array. Let's start by discussing the shape. The shape of an array represents a tuple of array dimensions. For a one-dimensional array, the shape would be a tuple of only one value n, where n is the number of elements in your array. For a 2D array, the shape would be nm, where n is the number of rows and m is the number of columns. In the last video, when you created your array with the arrange function, the array from 1 to 3, you actually, not knowingly, created a one-dimensional array whose tuple representation would be written like so, a tuple of one value 3, 3 representing the number of elements in your array. This one-dimensional array, this vector, is often used in mathematical operation. Typically in this course, we'll be dealing with higher dimensional arrays. How do we create a multi-dimensional array? Well, back to Jupyter Notebooks, recall that arrange is equivalent to Python's range function, but returns an array rather than a list. Let's make use of it again to create a 3x3 NumPy array by first importing NumPy as np to access all the submodules and functions from NumPy through this alias np. We'll make a variable x is equal to arrange np.arrange 3, which creates an array of 3 elements ranging from 0 to 2. Note that this is equivalent to writing 0 to 3, but by omitting the 0, it's assumed that you're specifying a start integer of 0 up until your stop integer of 3. Your array will therefore have 3 elements, ranging from 0 to 2, since the stop integer 3 is exclusive. Set y equal to the same thing, np.arrange 3, and do the same thing for z. All of these arrays are one-dimensional, each containing 1 row and 3 columns. However, if we were to combine them together, we'd get 3 rows and 3 columns, thus a 3x3 array. We can do that by declaring multi-array is equal to, we'll create our 2D array with the array function np.array. This function requires an object exposing the array interface. In essence, something that's array-like, whose method returns a sequence. A Python list will work just fine. We want our array to then combine all 3 arrays x, y, and z. Based on what we passed into our array function, the output of this, what's returned, will be an array object that satisfies the specified requirements. Go ahead and print multi-array, and it outputs 3 rows of data. Each row has 3 columns. We can further show this by printing the shape of the array. Print multi-array dot shape. And it outputs a tuple indicating a 3x3 array, 3 rows and 3 columns. If I remove the x, we're then missing a row, thereby outputting a 2x3 array, such that we still have 3 columns. Alternatively, we could have created our one-dimensional arrays with np.linspace rather than arrange. This is similar to arrange in the sense that np.linspace, first let's write it down, it has a start and a stop index. They both have it. That is, if I specify a start index of 1 and a stop index of 10, it's going to grab numbers from 1 to 10, and the third number indicates the amount of samples that we want to generate between 1 and 10. Let's assume I want to grab 50 samples. If we print w, we get a one-dimensional array of numbers between 1 and 10. More specifically, it returns 50 numbers, and all numbers are evenly spaced. If we make this into 100, it gives back 100 numbers, all evenly spaced from 1 to 10. Do not confuse this with arrange's step integer. On a new cell, copy and paste what we have. I will call this B. B is equal to np.arrange. And if I indicate a step of 3 and have the numbers go from 1 to 30, the sequence is still going to be from 1 to 29, except that it would grab every third element in the sequence, whereas with linspace, this third argument specifies how many elements we want from 1 to 30. If we change it to linspace, it would grab 3 numbers from 1 to 30 that are all evenly spaced. So, take-home message. With arrange, this indicates step size, whereas with linspace, it refers to the amount of samples between your range. If I put this back to what it was, and remove the step size for now, just to make things more intuitive, notice how with arrange, the stop integer, 30, is excluded from the sequence. It goes from 1 to 29, not from 1 to 30, whereas with linspace, it does include the integer at which we're stopping. It indeed goes from 1 to 10. It would still go from 1 to 30 if we specified it as such. Well, the thing with that is that linspace has a fourth argument. It's a bool value, which is by default true. If we set it to false, then it's not going to go all the way to 30. It is excluded. This was just to get you familiar with a function that creates 1D arrays aside from arrange, but now let's quickly move on to indexing. We'll go ahead and delete this cell, this one as well, and we'll go back to our previous train of thought. In the last video, we indexed a one-dimensional list using a single integer. The notation for indexing a one-dimensional array is the same, and it is also the same thing for a two-dimensional array, such that we can still write multi-array, and inside these brackets is where we're going to indicate the index that we want to access. Although, since this is a two-dimensional array, indexing is done with 2 integers, not just 1. The first integer, we're going to call it n, indicates which row we want to access, and the second integer, m, indicates which column. We'll start by changing the range of our second array. It will go from 3 to a stop index of 6, so from 3 to 5, and also changing the range of our third array. It will go from a start integer of 6 to a stop integer of 9, so it's going to have a sequence going from 6, 7, 8. Accordingly, if we print out the multi-dimensional array, it seems that I forgot to put back my x. It would indeed output 0, 1, 2, 3 all the way to 8. Each row containing 3 elements. Suppose I want to access the number 0. For our 3 by 3 array, rows are indexed from 0 to 2. 0 is located in the first row, which would correspond to row 0. Columns in this case are also indexed from 0 to 2, such that 0 is also in the first column, column 0. If we output this, we get back a value of 0. The value 5 is on the second row, third column. It is therefore on row 1, column 2. Output the value, and it results in a value of 5. Clearly, selecting elements from an array is very simple, and if you've done the Python crash course, you'll realize that it's very similar in how we index lists. Except now we have 2 integers, which represent the indices of the item in the array. If this array was 3-dimensional, at the moment it's 2-dimensional, as you can see by its shape. If it was 3-dimensional, you would require an extra integer. Finally, before we end this discussion, recall that NumPy arrays are generally homogeneous, such that items composing the array are generally, as you can see, all of the same type. We declared a homogeneous array. Therefore, the elements of that array can be described by the data type object, dtype. That is, by printing on a new cell, print multiarray.dtype, it outputs int64, which indicates that all the elements of my array are 64-bit integers. Many functions like array, like arrange, have a data type argument, which allows you to specify the type of your output array. In our case, by default, a type int64 was inferred, 64-bit integers. We can specify the type of the output array to be something like int16. That is, dtype is equal to numpy.int16. If we run this cell, I forgot my comma, and run the subsequent cell, the element types are now of integer 16. It could even be an unsigned integer of uint8, for example. And now all element types are uint8. The point I want to make is that the Python integer and float type that we saw in the crash course, they are not enough for scientific computing, whereas NumPy has a lot more numerical data types than Python, whose precision depends on memory requirements, such that the numerical types typically end with a number that indicates the number of bits associated with the type. That is all we're going to cover for the NumPy array object, as well as selecting elements from an array. In the next video, we'll look at how we can slice arrays.